Hello students, welcome to the class. So in the previous class, we have discussed about the kinetic theory of gases, right? What are the postulates? So we have seen that every gas, any gas, it is made up of large number of small particles, which are called molecules. They are moving with high velocities in all possible directions. When you consider the volume of individual gas molecules, it is negligible as compared to the volume of the entire gas. Gaseous molecules, the collisions, when they collide with each other, the collisions are perfectly elastic. We have seen, that is, there is no net loss of energy. Particles of gases are always in constant motion. Collisions of the gas molecules perfectly elastic. At particular temperature, distribution of the speed between gaseous particles remains constant because average kinetic energy of the gaseous molecules is directly proportional to absolute temperature. And even we have seen the kinetic equation on the basis of these postulates. What was the kinetic equation we have seen? We have seen the kinetic equation, that is PV is equal to 1 by 3 mNv square. That is nothing but RMS, wherein RMS stands for what? It stands for root mean square velocity. Yes, and in calculating this kinetic energy, we have come to the equation, that is kinetic energy of 1 mole of gas. 1 mole of gas at standard temperature and pressure. We had seen the equation. It was 3 by 2 RT. It was 3 by 2 RT. Yes. So this was what we had seen. Apart from that, see, kinetic energy, it is directly proportional to temperature. From this equation only we come to know what is root mean square velocity. Root mean square velocity, because we come across these questions on this also. So root mean square velocity, you can denote it as VRMS, root mean square velocity. That is equal to root of 3 PV by M. You don't have the derivation for all these, or you can write it as, we know that PV is equal to RT. Therefore, I can also write it as the velocity is equal to 3 RT by M, where M is molecular mass, T is temperature, P is pressure, V is volume, or it can be also written as, we know that it can be also written as root of 3P by D. Yes, 3P by D. Yes, where D is density. Okay. Then we have average speed. We have the calculation for average speed here. So average speed, it is denoted by C bar. That is equal to what? The formula for average speed is root of 8 RT upon pi M. This is the formula for average speed. Most probable velocity of the molecules according to kinetic theory of gases. According to kinetic theory of gases, it is written as C asterisk, and that is equal to root of 2 RT upon M. So these all are the equations. And here we have seen average kinetic energy is equal to, it is written as EK. You can write it as EK also. Average kinetic energy 3 by 2 nRT. Yes. For 1 mole, it is N is equal to 1. So I keep it as nRT. So these are the different formulae. These are the different formulae for calculating. This is for average speed. Yes. And then this we have for most probable velocity. And this we have for average kinetic energy. We have seen it. And this is the equation for root mean square velocity, RMS, root mean square velocity. So with this, we will move on to the next part. That is, we have seen deviation from ideal behavior. Yes, deviation of behavior of real gases from ideal behavior. See, we have discussed this. An ideal gas, it is composed of randomly moving minute particles, which are called as molecules, according to kinetic theory of gases, which undergo elastic collisions. That means there is no net loss of energy. Real gases are the ones which do not follow ideal relations of the gas laws. They do not follow ideal behavior under all conditions of temperature and pressure. The deviation of real gas from ideal behavior occurs due to the assumption that, why the deviation occurs? It occurs due to the assumption that If pressure increases, the volume decreases. Because suppose you have considered, let us say that we have seen all the laws, right? So what the law says, okay, let me say this is some molecules I have taken here. Okay, so let us assume that we have some molecules taken here. And this is the volume occupied by these molecules. Suppose I place a piston over here and I apply pressure. If I apply pressure, what was the assumption? Yes, according to Boyle's law, the assumption was when you increase the pressure, the volume decreases. That means the assumption is that the volume becomes less. The volume decreases. The volume will approach a smaller number but will not be zero. Because we know that the molecules will occupy some space that cannot be compressed further, yes or no? If you increase too much pressure, volume, will it become zero? No, it will not become zero, because the molecules, there is intermolecular space, therefore they will not, the volume will not become zero, they will occupy some space and therefore they cannot be compressed further. So this experimental observation of gases correctly corresponds to the theoretical model. The difficulty arises when we test to the extent of the relation. This relation, when you go to test for real gases, there is difficulty. That means at all temperatures and pressures, the real gases don't show this behavior. The ideal gas equation, it is followed to depict actual pressure volume temperature relation of the gases. To have a check on these points, let us plot. Let us see a plot of, yes, here we have, let us see this plot of pressure versus pressure into volume, product of pressure into volume versus pressure volume, pressure you consider. Yes, so PV versus P graph will be a straight line parallel to the x-axis for ideal gas. Can you see here? It will be a straight line parallel to the x-axis. Can you see this line for ideal gas? It will be a straight line parallel to the x-axis. Now, what do we understand by all these gases? These are not ideal gases. These are real gases. So, the above figure, what graph you are seeing here, it is constructed from actual data for some gases, say carbon monoxide, CH2, H2, and then helium. Yes, for these gases, it was constructed at 273 Kelvin. Look at this graph. What do we understand? What do we understand from this graph? We get so much of information, students. Yes, so this is at constant temperature. It is an isotherm. Okay. At constant temperature, the plot of PV versus P is not a straight line for real gases. These are all our real gases, and it is not a straight line. There is significant deviation from ideal behavior. Can you see the significant deviation? Yes, from ideal behavior. In case of hydrogen and helium, if you see in case of hydrogen and helium, if the value of P increases, see, P is increasing in this direction. If the value of P increases, the value of PV is also increasing. In other cases, like CH2, in other cases, like this is CH4, I'm sorry, this is methane and carbon monoxide, if you see, first it is decreasing. As P is increasing, the value of PV, product of PV, pressure versus pressure into volume, it is first decreasing. That means, can I say it is showing negative deviation? This is increasing means positive deviation. Okay, first it is decreasing means what? It is first showing negative deviation from the ideal behavior. Yes, the increase in pressure decreases the value of P and reaches a minimum value. It reaches certain minimum value. For CH4, it is reaching this minimum value. For CO, it is reaching this minimum value. After it reaches this minimum point, please observe the graph. After it reaches the minimum point, PV value again starts increasing. It crosses the line for ideal gas and then shows a positive deviation. Can you see? It crosses this ideal gas line and then shows a positive deviation. Positive deviation, continuously it is showing positive deviation. So it can be said that real gases do not follow ideal gas equation at all temperatures and pressures. Here I have plotted against pressure at constant temperature. So it is not showing, it will not show real gases. These are all real gases. So real gases do not follow ideal gas equation at all temperatures and pressures. the deviation of the real gas from ideal behavior is also seen when you plot a graph of pressure versus volume also. I have shown you in one of my graph. When you plot a graph of pressure versus volume, this graph I am speaking about. See, deviation is seen here also. Yes or no? It is seen here also. The graph of pressure versus volume should coincide from the experimental data for ideal gas. How it is for ideal gas, it should be same for real gas. Theoretical data, what it is there, it is calculated by Boyle's law. According to Boyle's law, we say that the gases should behave like that. As pressure increases, volume decreases. So that is theoretical graph which was plotted. And our actual, what practically we do, that should coincide with that curve, but it is not coinciding. So it is being observed that, what is being observed is, at high pressures, the measured volume of the gas is more than the calculated volume. Yes, it is more than the calculated volume. But at low pressures, the calculated value and the measured value are almost same. Yes. So at what conditions? At low pressure, the calculated value and measured value are almost same. Calculated and measured values, they approach each other. So it can be stated that real gases, they do not follow Charles' law, Boyle's law, and Avogadro's law perfectly under all conditions of temperature and pressure. They follow this law at very low pressure or at extremely high temperature. At very low pressure and at extremely high temperature. So this is deviation of real gases from ideal behavior. Yes, so they are found to obey the laws fairly if the pressure is very low and the temperature is very high. And those gases are called what? They are called as real gases. So you have a convenient way of showing this deviation of real gases from ideal behavior. There is a way to show the deviation of real gases from ideal behavior. Yes, and that convenient way is nothing but compressibility factor. It is nothing but compressibility factor. Yes, so here we have seen. Yes, compressibility factor. So what do we understand? What explanation does this compressibility factor tell us? So it is difficult to determine quantitatively the deviation of a real gas from ideal behavior from when you plot a graph of P versus V isotherm curve or PV versus P or pressure or temperature you take. So compressibility factor may be defined as to explain the deviation of real gases from ideal behavior can be measured in terms of compressibility factor, which is denoted as Z. So Z is equal to what? PV is equal to PV by nRT. This is the formula for compressibility factor. Now you see, we know that ideal gas equation, they obey the equation PV is equal to nRT. Now, how do we explain this based on compressibility factor? They say Z is equal to PV upon nRT. If Z is equal to 1, it is for ideal gas. It is for ideal gas. Z is equal to 1. So if Z becomes 1, then you can see here 1 is equal to PV upon nRT. Correct? And take this nRT this side, we can write PV is equal to nRT. Therefore, compressibility factor for an ideal gas, a value of compressibility factor for an ideal gas is 1. Z is equal to 1. And for real gases, Z is not equal to 1. It may be greater than 1 or it may be less than 1. So if Z is greater than 1, we say real gases show positive deviation from ideal behavior. Yes, if Z is greater than 1. It refers to positive deviation. It means that, what does this mean? It means that gas is less compressible. Gas is less compressible. So positive deviation. from the expected. Example we have seen in the curve, in the graph, helium, H2, positive deviation. If Z is less than 1, it means that it's showing negative deviation. It means that gas is more compressible. Gas is more compressible. It is more compressible. For example, negative deviation. First it came down and then it increased, right? For carbon monoxide and for CH4. Yes, it was actually carbon dioxide, if I'm not wrong. It is carbon dioxide. So compressibility factor will tell us what the deviation from ideal behavior. And for ideal gases, compressibility factor Z is equal to what? Z is equal to 1. For ideal gases, Z is equal to 1. For ideal gas. And for real gas, Z is not equal to 1. So Z might be greater than 1. If it is Z greater than 1, it means what? Yes, if Z is greater than 1, it refers to positive deviation. And if Z is less than 1, it refers to negative deviation. It refers to negative deviation. So this is about compressibility factor. Therefore, I can say here, I can write it as PV is equal to ZNRT, correct? PV is equal to ZNRT, or I can also write it as Z is equal to PV upon nRT. Yes, so here V becomes what? V becomes molar volume. So P into molar volume upon nRT. Like this also I can write. Yes, I can write it like this. Yes, this is more suitable for quantitative description of deviation of real gas from ideal behavior. Yes, greater is the departure of Z from unity. Greater is the deviation. Yes, I can write it here. Greater the deviation of Z from 1. More is what? More is deviation from ideal behavior. More is the deviation from ideal behavior. Therefore, we can say Z is equal to 1. The gas is ideal at all temperatures and pressures. So, in case of N2, if you see in case of nitrogen, the value of Z is close to 1 at 50 degrees Celsius. At 50 degrees Celsius, the value of nitrogen, the value of Z is close to N. What does this mean? This temperature at which real gas exhibits ideal behavior for considerable range of pressure is known as, certain temperature. It is known as what? It is known as Boyle's temperature. Boyle's temperature. Yes, represented as TB, or you can say Boyle's point. So what does this mean? I just gave you example. Nitrogen, the Z value approaches, it is close to 1 at 50 degrees Celsius. That means almost at this temperature, nitrogen is showing ideal behavior. Yes, so at this temperature, for a considerable range of pressures, it will show ideal behavior. That means its curve will go with the ideal curve. This is ideal curve. So nitrogen, at a temperature say 50 degrees Celsius, the curve will go with nitrogen with ideal behavior over a range of pressures. So the temperature at which, how do you define Boyle's temperature? It is the temperature at which real gas exhibits ideal behavior. So temperature at which real gas exhibits ideal behavior over a range of pressures. over certain range of pressure is known as Boyle's temperature, denoted as TB, or you can call it as Boyle's point. You can call it as Boyle's point. Yes. If Z is greater than 1 means what? The gas, it shows positive deviation. It means it is less compressible. It is less compressible than expected from ideal behavior. It shows positive deviation. Yes, at usually high pressure. That is, if Z is greater than 1, imagine with this. Z is more than 1 means what? Means PV is greater than RT. Correct? PV is greater than RT. If Z is less than 1, it shows negative deviation. That means it is more compressible. It is more compressible. Yes, and shows a negative deviation. Yes, therefore, why it is like that? If Z is less than 1, PV will be less than RT. Please do remember this. These points are very important. Yes, this is remembered. Ideal gas. Yes, greater than 1, positive deviation, less compressible. PV is greater than RT. Negative deviation, Z is less than 1, more compressible. PV is less than RT. Examples for Z greater than 1, you have here, I will mention it. You have hydrogen, you have helium, correct? At all pressures always show positive deviation. Negative deviation, yes, it is carbon dioxide and ammonia, CH4, yes, negative deviations. Carbon dioxide is such a gas that it shows both positive as well as negative deviations. Positive as well as negative deviations. Now the question is, all this scenario is understood. Okay, fine. Negative deviation is there, positive deviation. Now the question is, why there is deviation? Why real gases? See, understood. It shows deviation, we got to know now. When we looked at this graph, we understood that deviations also. And we, from this compressibility factor, point is clear. So see, helium and hydrogen, positive deviation, less compressible, more compressible, right? Then, less compressible. Carbon, this is, please make a correction here. This is carbon dioxide and this is methane. Okay, so carbon dioxide and CH4, negative deviation, it decreases. So negative deviation means gas is more compressible. Gas is more compressible. Okay, so from this graph, we got to know many things. Now the question is, why this deviation is seen? Why real gases show this deviation? Why don't they obey? Why do they obey or ideal gas behavior only at very high temperature and very low pressure? Why not at all temperatures they also exhibit ideal gas behavior? The reason is there is mistake in the kinetic theory of gases only. Yes, we have seen so many postulates of kinetic theory of gases, right? So many postulates we came across. In those postulates, there are some corrections to be made. Now, what are those corrections? So why? Causes for the deviation. Causes for deviation from ideal behavior. From ideal behavior. What are the causes? The ideal gas laws, they are derived from kinetic theory of gases, right? Which is based on 2 points. What is the 2 points? First point, I had told you to remember. The first point says that the volume occupied by one molecule, volume of one molecule, we have seen this point, is negligible as compared to volume of gas, entire gas molecules. Second, this is a postulate of kinetic theory. Second point is, molecules do not exert any force. There is no force of attraction between the molecules. No forces of attraction between the molecules. Yes, these were the 2 points what we have seen. Along with many points, these were also 2 points what we had seen, right? The molecules exert no force of attraction upon one another. It is because neither of these two assumptions can be regarded as applicable to real gases, that the later show departure from ideal behavior. So in order to rectify this mistake, in order to rectify these errors, yes, caused by ignoring the intermolecular force of attraction. See, just imagine if I reduce the volume of one molecule is negligible as compared to volume of gas. By applying pressure, I'll go to Boyle's law only. If I apply heavy pressure, what will happen? All the molecules will come nearer. volume gets reduced. When volume becomes very less, can I say volume of one molecule is negligible? No, the volume of one molecule is also considerable there. Yes, even no force of attraction between the molecules, they say. When you apply high pressure, we know that by Boyle's law, pressure is inversely proportional to volume. Why it becomes inversely proportional to volume? Charles' law says volume is directly proportional to temperature. Yes. Why is it so? When you apply pressure, the volume, the intermolecular distance decreases. When the intermolecular distance decreases, intermolecular force of attraction increase. What our kinetic theory of gases says, there is no force of attraction between the molecules, which is absolutely wrong. Yes or no? Understanding, when the intermolecular force of attraction increase, when you apply pressure, the molecules will come closer, intermolecular force of attraction will increase. That's the reason gas gets converted to liquid, and we have a practical example for it, right? But the gas, water vapor becoming water, we have seen practically. Water becoming solid, we have seen practically. Why is this happening? That means there is some mistake here. Some things have to be rectified, and that was rectified by van der Waals. Yes, through his equation, which was called as van der Waals equation. Yes, these rectifications were done by van der Waals through his equation. Yes, so let us first see what is it all about. Van der Waals equation. So here this equation. Yes, so what was this all about? There is no force of attraction between the molecules of gas was one of the postulate of kinetic theory of molecules. Volume occupied by the gas molecules is negligible in compared to the total volume of the gas. This was another. Yes. So about two assumptions of the kinetic theory of the gases was found to be wrong at very high pressure and at very low temperature. Yes, it was found to be wrong at very high pressures and at very low temperatures. Getting my point? So this was considered by van der Waals. And what did van der Waals do? He gave the equation. He gave the equation. He gave this equation. Now let us try to understand what it is all about. Okay. Fine. So to rectify the errors caused by ignoring the intermolecular force of attraction and the volume occupied by the molecules, van der Waals modified the ideal gas equation only. He modified the ideal gas equation. Yes, so he gave the equation as P plus n square A by V square into V minus NB is equal to nRT. This was for n moles of gas. If you take 1 mole of gas, what equation was shown there? That comes P plus A by V square, V minus B is equal to RT. So is it of the form PV is equal to nRT? So he made a correction. This what term you are seeing, P plus n square by A, n square A by V square, that is the pressure correction for molecular attraction, and V minus NB, it is the volume correction for finite sizes, where this A and B are called van der Waals constants. Yes, whose values depend upon the nature of gas. Normally for a gas, A is very much more than B. Please do remember this. Yes, so van der Waals considered, he gave the equations. He gave these equations. So van der Waals derived the equation, the van der Waals equation derivation, it is based on correcting the pressure and volume of the ideal gases given by kinetic theory of gases. Yes, another, there is one more derivation also, it is based on same, but first of all, we'll just concentrate on this. So what kinetic theory had said, we had seen point masses without any volume, molecules have independent, having no interactions, there are no attractive forces, and undergo perfectly elastic collisions. See, when they are hitting the walls of the containers, pressure is exerted. Force per unit area is what is pressure. So he made these corrections. First, what he said, as the particles have definite volume, he said the particles possess definite volume. Yes, as the particles have definite volume available for their movement, as the particles have definite volume, I'm speaking the volume correction. As these particles have definite volume, the volume available for their movement is not the entire container. but it is less. So volume in the ideal gas is hence an overestimation, and it has to be corrected. It has to be corrected, and he corrected it. He gave the equation. What he gave the equation? V minus NB. This was the equation what he gave. Correct. Further, he said pressure in terms of pressure. He spoke in terms of pressure. So pressure correction he did. He did the pressure correction. And he gave this equation, P plus N square A by V square into V minus NB is equal to what? It is equal to nRT. It is equal to nRT. So this equation was being given by van der Waals. This is nothing but a slight correction in our ideal gas equation. A slight correction in our ideal gas equation. Correct? So this was the equation given. Again, the volume of the gas, if you see, it will be larger compared to the volume of the molecules. So N and B were the terms used. So hence the volume correction also will be small and it will be negligible. So as the correction factor becomes negligible, pressure and volume of the real gases will be equal to that of ideal gases. Interestingly, all real gases behave like ideal gases. All real gases behave like ideal gases at low pressures and high temperatures. At low pressures and high temperatures. Yes, I repeat, what all corrections he made? He made two important corrections. Yes, the two important corrections were, in case of volume, what he said? He said that as the particles have definite volume, the volume available for their movement is not the entire container, but it is less. So he gave the correction as V minus B. So volume of the real gas is equal to volume of the container minus this correction factor. V is the correction factor. So volume of the container minus volume of the correction factor. And particles are not independent. They do interact. They do interact. Yes. Volume correction he gave. Then what about pressure correction? Gaseous particles, they also interact. For inside the particles, the interactions cancel each other. But the particles which are there on the surface and near the walls of the container do not have particles above the surface and the walls of the container. So there will be net interactions or pulling of the bulk molecules towards, that is away from the walls of the container. So the particles which are at the surface and at the container, walls of the containers, there will be force experiencing. The molecules present here, they will experience a net interaction away from the walls. They will hit the walls with less force and pressure. Hence, real gases, hence in real gases, the particles exhibit lower pressure than shown by ideal gases. And that was the pressure correction done. The pressure correction, P plus A by V square. So the A is the correction factor. A is the correction factor. So A and B are called what? They are called as van der Waals constants, and they contain positive values. The constants are the characteristics of individual gases. It depends upon the nature of gas. Okay, when gas is ideal or that it behaves ideally, then both the constants will be zero. Both the constants will be zero if it behaves ideally. Yes, so this is what it is, the correction factor. It is the correction factor. So constant A, if you see, it is an indirect measure of magnitude of attractive forces between the molecules. This constant A, what you are seeing, it is what? It is the measure of attractive forces between the molecules. So we can say greater the value of A, greater the value of A, more easily the gas can be liquefied. More easily the gas can be liquefied. These are the points to remember in van der Waals equation. Yes, so easily liquefiable gases you can consider. Yes, SO2 is most easily liquefied. Then you have NH3. Then you have H2S. Then you have CO2. Yes, so easily liquefiable gases have high values than permanent gases, like for example N2, O2, H2 and helium. What is the unit of A? The unit of A is pressure correction, atmosphere, liter square per mole square, per square mole. Yes, this is the unit for A. SI unit, you can take it as Newton m raised to 4 per mole square. This is the unit for A. Then what is the correction of B? Yes, what does this indicate? It is also co-volume. It is also what? Co-volume. So greater the volume, greater the value of B. Greater the value of B means what? Larger is the size. Larger is the size. And smaller is compressible volume. Compressible volume. Yes. So B and A are the correction factors. Value unit of B is, SI unit of B is cubic meter per mole. Volume correction, right? So cubic meter per mole. The two van der Waals constants and Boyle's temperature. I hope you remember what is Boyle's temperature. It is the temperature at which real gas behaves like ideal gas over a range of pressures. If you want the relation between the two constants A, B and Boyle's temperature, here is the relation. TB, that is Boyle's temperature, is equal to A by BR. A and B are constants. R is universal gas constant. R is universal gas constant. Yes. And here we have certain terms to understand. Van der Waals equation at different temperatures and pressures. First one, very, very important equations. When pressure is extremely low. When pressure is extremely low, what is the equation? The equation is P plus A by V square V minus B is equal to RT for 1 mole, okay, is equal to RT. Yes, or you can even write it as PV is equal to RT minus A by V plus PB plus AB by V square. Okay, second one, when pressure is extremely high. When pressure is extremely high, the equation is PV is equal to RT plus PB. I'll write it properly. PV is equal to RT plus PB. RT plus PB. Or I can write it as PV upon RT is equal to 1 plus PB upon RT. 1 plus PB upon RT. Divide all of them by RT. PV upon RT is equal to 1 plus PB upon RT. Or what is PV upon RT? PV upon RT is nothing but Z. Z is equal to 1 plus PB upon RT. This is when pressure is extremely high. And Z is what? Compressibility factor. Okay. Next, third term. When temperature is extremely high. When temperature is extremely high, the equation is PV is equal to RT. See, at extremely high temperature and at extremely low pressure, it obeys ideal behavior. Okay, we'll see here. Next, fourth point, when pressure is low. When pressure is low, what will be the equation? Same equation, P plus A by V square, we have seen here. P plus A by V square, V minus P is equal to RT. This can be also written as PV is equal to RT plus PB minus A by V plus AB by V square. I can write it like this also. Or it can be written as PV upon RT is equal to, dividing all of them by RT, 1 plus, or I will separate it, simplify it completely, and I'll write the equation 1 minus A by VRT. A by VRT. That is nothing but what is PV by RT? Z is equal to 1 minus A by VR. See, compressibility factor, it varies. Yes, it varies. Is that right? So this is all about van der Waals equation. What is the merits? It holds good for real gases up to moderately high pressures. Yes, and the equation represents the trend P plus A by V square into V minus P is equal to RT. It represents the trend of isotherms representing the variation when you plot the graph of PV versus P. Correct? So van der Waals equation, it is useful in obtaining the reduced equation of the state when you know the constants A and B. Yes, these are the merits. What is the limitation? It is appreciable deviations at very low temperatures and very high pressures. You can see the deviations. Yes, so this is about the van der Waals equation. So here the equation is given for 1 mole of gas, P plus A by V square, V minus P is equal to RT. Yes, it is equal to RT. Moving to the next term, that is liquefaction of gases. Liquefaction, as the name suggests, converting the gases into liquids. So liquefaction, it is having a very wide importance. Thomas Andrews investigated this liquefaction, complete relationship between volume and pressure. You can see there, volume, temperature also, volume and pressure also, all these equations, the graph what you are seeing. After more research on his relationship, it was found that at very high temperature, isotherm is similar to that of ideal gas. It is similar to that of ideal gas, the curve what you are seeing. Yes, if you observe this curve. So liquefaction of gases can be achieved either by lowering the temperature or increasing the pressure. So what happens when you lower the temperature? Since temperature is directly proportional to kinetic energy, when you reduce the temperature, what will happen? The kinetic energy of the molecules will decrease. And when you increase the pressure, the molecules will come closer. Volume reduces. Therefore, it gets converted to liquid. That is the concept, liquefaction. Observe this graph, what I have shown. Yes, if you see here, it is shown for carbon dioxide. This graph is for carbon dioxide. Yes, carbon dioxide is in gaseous state up to a pressure, say 73 atmosphere. Yes, I'll explain it here only. Up to this temperature, pressure, carbon dioxide is gas existing in gaseous state. And at a temperature, how much it is? At a temperature of this curve, so it is 30.98. So the pressure 73 atmosphere is called critical pressure. It is mentioned here. It is called critical pressure. And temperature 30.98 is called critical temperature. So what do we mean by critical pressure and critical temperature? See here, critical temperature denoted by Tc. It is defined as that temperature above which gas cannot be liquefied, however high the pressure may be applied. So above this temperature, for carbon dioxide, I just said it is 30.98. Above this temperature, gas cannot be liquefied. Yes, so gas cannot be liquefied further. That is called critical temperature. And it is given by 8A upon 27 Br, where A and B are van der Waals constants, R is universal gas constant. Similarly, we have critical pressure. These are all called as critical states. So critical state means what? A state for every substance at which vapor and liquid states are indistinguishable. You cannot distinguish whether it is in vapor state or it is in liquid state. Yes, it is called critical state. So critical temperature means what? Suppose for carbon dioxide, critical temperature is 30.98. What does that mean? It means that above this temperature, you cannot liquefy that gas. Gas cannot be liquefied, however high pressure you apply. And it is calculated 8A by 27 Br. A and B are van der Waals constants. R is universal gas constant. Critical pressure. It is the minimum pressure which must be applied to liquefy a gas. So what do you mean by critical pressure? The minimum pressure which must be applied to a gas to liquefy it at its critical temperature. At its critical temperature only, a gas can be liquefied by applying minimum pressure. And PC is equal to what? A by 27 B square it is. It is B square. A by 27 B square. Again, A and B are constants. So it is B square here. B square. Okay. Then critical volume. When you use critical temperature and critical pressure, what you do? You will get the gaseous state into liquid state. The volume occupied by 1 mole of gas at critical temperature and pressure is called critical volume. And you can even calculate critical volume also. Vc is equal to 3b. Critical volume is equal to 3b, where b is van der Waals constant. Yes. So these are critical states. For example, for carbon dioxide to liquefy, critical temperature is 30.98. Means what? Above 30.98, you cannot liquefy carbon dioxide. Above 30.98 degrees Celsius, you cannot liquefy carbon dioxide. Critical pressure is 73.8 atmosphere. That means at this pressure, yes, the gas should be at 30.98 temperature. At this pressure, carbon dioxide gets liquefied. Volume is 95 cc per mole. That means when you add critical temperature and critical pressure, the volume of carbon dioxide, 1 mole of carbon dioxide at critical temperature and pressure is 95 cc per mole. Understood? Even you have critical compressibility factor. It is denoted as ZC. ZC is equal to, we know PV by nRT. So PC into VC upon R TC. So critical pressure, critical volume, critical temperature. And that is equal to 3 by 8. When you use all the formulae, 3 by 8, that is nothing but 0.375. 0.375. This is critical compressibility factor. Yes, a gas behaves as van der Waals gas if its critical compressibility factor is equal to 0.375. Yes, a substance in the gaseous state. A substance in the gaseous state below critical temperature is called vapor, and above critical temperature it is called gas. Yes, below critical temperature it is called vapor, and above critical temperature it is called gas. So this is all about the critical states. Very important to remember. Yes, critical states. You should be knowing what do we mean by critical states. Yes, so critical temperature, the temperature at which above which the gas cannot be liquefied. Yes, this is all shown here. For carbon dioxide it is. Yes, the critical temperature for carbon dioxide is 30.98 degrees Celsius. That means above this temperature you cannot liquefy the gas. The critical pressure is 73 atmosphere. Yes, you can see here 73 atmosphere. That means at this pressure, when the gas is at a critical temperature, it can be liquefied. And critical volume at critical temperature and critical pressure for carbon dioxide, it is how much? It is 7. How much we had discussed? We had seen the volume occupied is 93 something, correct? That is the volume. So if you look at this graph, carbon dioxide, it is in gaseous state up to 73 atmosphere. That's the reason I said below critical states, it is in gas. Above critical states, it is in vapor. It is in vapor and can be liquefied. So it converts to liquid state at 73 atmosphere and 30.98 degrees Celsius. And they are called critical pressure and critical temperature respectively. So the temperature 30.98 is called as critical temperature. At this critical temperature and critical pressure, the volume of 1 mole of gas is known as critical volume. Further, if you raise the pressure, rise in pressure, what it does, it compacts the liquid. Yes, so carbon dioxide curve you can see depict the compressibility of the liquid. The erect line in the graph, what you are seeing, the erect line in the graph, yes, it shows the isotherm of the liquid. Yes, at particular temperature. At temperature below 30.98, behavior of the gas on further compression varies a different pattern. Okay, so at point B, you can see here, at point B, some part of carbon dioxide becomes liquid. There is slight rise in the temperature. So some part of carbon dioxide becomes liquid and some part becomes gas. With more compression of the liquid, the pressure do not change. Both liquid and gaseous form of carbon dioxide, it exists at point B. Both liquid and gaseous form of carbon dioxide exists at point B. All gas is compressed at point C. All gas is compressed at point C. Yes. So compression of a gas changes the volume from V2 to V1. From V2 to V1. See, there is change in volume. From V2 to V3, I'm sorry. V2 to V3 here. Correct? Yes. And which gives rise in the pressure from P2 to P3. So pressure increases. This is V3 actually. This is V3, V2 to V3. And pressure increases to 73 picometers. Sorry, 73 atmospheres. Yes. So point A and D. Can you see here? Point A and point D. They represent the gaseous state and liquid state. So this is gaseous state and this is liquid state. Yes. And a point under dome shape. This point, it represents the liquid and solid shape in equilibrium. So all the behavior shown by carbon dioxide is true for all the gases. It is true for all the gases. So this is about liquefaction of gas. So what do we explain here in liquefaction of gas? A gas may be liquefied by cooling or by the application of high pressure, or you can say combined effect of both. Cooling, lowering the temperature, or by application of high pressure. The first successful attempt for liquefying the gases was made by Faraday. It was made by Faraday. Gases for which the intermolecular force of attraction are small. So, for example, H2, say N2, argon, intermolecular force of attraction are small. They have low values. They all have low values of critical temperature. Yes, and cannot be liquefied by the application of pressure. And these gases are known as permanent gases because their critical temperature is low. They are known as permanent gases. While the gases for which intermolecular forces of attraction are low. Okay. For gases where intermolecular forces of attraction are high, for example, you have NH3, you have SO3, SO2, water you have carbon dioxide. They have high values of critical temperature. High values of critical temperature and can be liquefied easily. Please do remember all these points. Liquefied easily. So low values of critical temperature, they are called as permanent gases. They cannot be liquefied. High values of critical temperature, they are called what? They are where their intermolecular forces are high. They are polar molecules. Yes, and they can be liquefied easily. And there are methods for liquefaction. Yes, Lenz's method is there. And you have Claude's method. What are the uses of liquefied gases? The liquefied gases compressed under high pressure, liquid ammonia, for example, liquid sulfur dioxide, they are used as refrigerants. Liquid ammonia and liquid sulfur dioxide are used as refrigerants. Liquid carbon dioxide, it is used in soda fountains. Liquid chlorine, it is used in bleaching and disinfectant. Liquid air, it is an important source of oxygen in rockets. Compressed oxygen is used in welding purposes. Compressed helium, it is used in airships. Yes, so these are all the applications of liquefaction of gases. Applications of liquefactions of gases. Okay. Applications of liquefaction of gases. So this is liquid state. What are the characteristics? We know the intermolecular force of attractions are strong. They have definite volume but irregular shapes. Yes, we know all the properties. Molecules of liquids are held by intermolecular forces of attractions, right? Now, what do we mean by vapor pressure? The pressure exerted by the vapor of a liquid at a particular temperature in a state of dynamic equilibrium is called vapor pressure. Now, you can see here, suppose you are boiling this liquid. Yes, bubbles cannot be formed since this is just evaporation. This is evaporation, this is boiling. When evaporation is occurring, it is the surface phenomenon. Yes, bubbles will not be formed here. Why? Because here there is the heat to the surface. Whereas if you see boiling, the bubbles are formed here. It is a bulk phenomenon. It is the bulk of the phenomenon. So when boiling occurs, more number of molecules come into this phase. What is this phase called? This is liquid phase, and the above phase is what? It is gaseous phase, and that is called vapor phase. When more number of molecules come in vapor phase, they will be moving constantly. Heat is acquired, so kinetic energy will be more. So when they are moving randomly, they will collide and they exert pressure there. The pressure exerted by the vapor of a liquid above the surface of the liquid. Can you see? Above the surface of the liquid is called vapor pressure. It is called vapor pressure. Vapor pressure depends on two factors: nature of the liquid and temperature. It depends on the two factors. Then surface tension. It is defined as, what it is defined as? It is defined as force acting per unit length, perpendicular to the line drawn on the surface of the liquid. Perpendicular to the line drawn on the surface of the liquid. That is called as surface tension. SI unit of surface tension is Newton per meter. So what I am saying now, for example, the thing what I said, vapor pressure, then surface tension, viscosity, these are important properties of liquids. So vapor pressure, the pressure exerted by the vapor in equilibrium with its own liquid is called vapor pressure. Yes, so vapor pressure depends on what? It depends on temperature. How? As the temperature increases, the kinetic energy of the molecules increase. So as temperature increases, the vapor pressure of the liquid also increases. They will also increase. Then the nature of the liquid, that is nothing but volatility of the liquid. Vapor of volatile liquid. See, if I have honey and if I have water, which will come into vapor state more easily? It is water only. Yes. So volatile, honey is more, water is more volatile. So vapor of a volatile liquid is more, because that will convert into vapor phase most amount, whereas non-volatile it is less. So nature of the liquid as well as temperature. It does not depend upon the quantity of the liquid. I cannot say that if I take 1 liter of liquid or if I take 10 liters of liquid, in case of 10 liters there is more vapor pressure. No, it does not depend upon the quantity. It depends upon the nature and temperature. Therefore, I call vapor pressure as the intensive property. Intensive property means what? It does not depend upon the quantity. It does not depend upon the quantity of the liquid. Is that right? Okay. Then what do we mean by boiling point? The temperature at which the vapor pressure of the liquid becomes equal to the external pressure. Yes, the temperature at which the vapor pressure of the liquid, that is pressure over the surface of the liquid, becomes equal to the atmospheric pressure, that is external pressure. External pressure. Atmospheric pressure is external pressure. That temperature is called boiling point. Yes, if you take at 1 atmosphere pressure, boiling temperature is called normal boiling temperature. Normal boiling point. And it is 100 degrees Celsius for water. Example. If the pressure is 1 bar, instead of 1 atmosphere, if the pressure is 1 bar, then it is called standard boiling point. Standard boiling point. And it is 99.6 degrees Celsius for water I am speaking. Understanding? 99.6 degrees. So that is called standard boiling point. Coming to the next one, surface tension, force acting per unit length perpendicular to the line drawn to the surface piece. So it is the characteristic property of a liquid. I can show it here. You can see here. So it is the characteristic property of the liquid. The surface tension is due to unbalanced force experienced by the molecules at the surface. Now see, if the molecule is in the bulk here, can you see this? If the molecule is in the bulk here, it will experience force in all the directions. In all the directions. So it is balanced. But if the molecule is at the surface, what will happen? There will be unbalanced force experienced by the molecules at the surface. Correct? So in case of bulk of the liquid, each molecule is attracted equally in all the directions by the neighboring molecules. So it will, hence the net force experienced, hence the molecule will not have any net force experienced. Understanding? But if you consider it at the surface, these molecules are missing. So here the force will be unbalanced. The force will be unbalanced. This what you are seeing, the dark line, it is cohesive force to the neighboring molecules, attractive force to the neighboring. Whereas at the surface, that cohesive force is missing. Therefore, it is unbalanced. Because of this unbalanced force, when you draw a line perpendicular, can you see this perpendicular? So force directed at the interior of the medium, when you draw it perpendicular, acting on the unit length of the surface of the liquid is called what? Surface tension. So I can say surface tension, let me denote it as V, is equal to force by length. Force by length. So its unit is what? Newton per meter. It unit is Newton per meter. On what factors does this surface tension depends? It depends upon the intermolecular forces. If the intermolecular force of attraction are higher, surface tension is more. So I can say greater the intermolecular force of attraction, greater the intermolecular forces of attraction, higher is the surface tension. Surface tension is more. Surface tension is more. It also depends upon hydrogen bonding. Surface tension will be higher because of strong hydrogen bonding. If hydrogen bonding is strong, surface tension will be more. Third factor is it also depends on the temperature. With increase in temperature, surface tension decreases. Surface tension decreases and becomes, you can say, it becomes zero at critical temperature. It becomes zero at critical temperature. So surface tension, which the vapor pressure depends on temperature and nature of the liquid, whereas surface tension depends on intermolecular forces, hydrogen bonding, as well as temperature. Yes, greater the intermolecular forces of attraction, higher is the surface tension. Surface tension will be higher because of strong hydrogen bonding. And with increase in temperature, surface tension decreases and almost becomes zero at critical temperature. And what are the results of all these factors? Spherical shape of the drops, fire polishing of the glass, rise of liquid in the capillary tube. Capillary tube, the liquid rises. Small insects walking on water. See, the insects walk on water very easily. That is because of surface tension. Yes, so this is another physical property of liquid. Yes, another physical property of liquid. Then next is viscosity. Viscosity is what? Some liquids are viscous, we say. It is defined as the internal resistance to the flow possessed by the liquid. Liquid has got two important properties. One is fluidity. And another one is viscosity. Opposite to each other, both are. Fluidity is the tendency of the liquid to flow. Viscosity is the tendency of the liquid to stop the flow. So it is called as what? It is called as internal resistance of liquid to flow. So only you might have seen, if you place water on a tilt surface and if you place honey on another tilt surface, water flows faster, honey will flow slow. So we say honey is viscous. Yeah. So some liquids like water, petrol, ether, kerosene oil, they flow fast. While some other liquids like you take honey, you take castor oil or you take glycerin, it will flow very slowly, quite slowly. It means that, what does it mean? It means that every liquid has some internal resistance for the flow. And this differs from one liquid to another. So the internal resistance to flow possessed by a liquid is called what? It is called viscosity. What is the SI unit of viscosity? Internal resistance possessed to flow possessed by the liquid. So it is Newton per meter square. This is the SI unit for viscosity. Yes. So I can say greater the viscosity, more slowly the liquid flows. Yes or no? Glass is an extremely viscous liquid. It is so viscous that many of its properties resemble to solids. So only we say glass is pseudo-solid. Yes, it is pseudo-solid. Yes. So glass is extremely viscous liquid. Viscosity, greater the viscosity, more slowly the liquid flows. The viscosity of the liquids decreases as temperature increases. Why? So viscosity of liquids, it decreases as temperature increases. What is the reason? Because at high temperature, the molecules will have high kinetic energy, and therefore they can overcome the intermolecular forces. Kinetic energy is directly proportional to thermal energy. So they will overcome the intermolecular forces. They will overcome the intermolecular forces. Yes, that is all about viscosity. Yes, internal flow. The liquids which flow slowly have high viscosity, and the liquids which is due to stronger intermolecular forces and hence are said to be more viscous. Yes, when liquid flows, the layer immediately below it tries to retard its flow, while the one above it tries it to accelerate. Thus, a force is required to maintain the flow of the layers, and this is the expression given. Force is directly proportional to area of the contact, and this is how we give the expressions. So with all these properties, we come to certain conclusions. So what are the conclusions that we come across? Yeah. See, rate of diffusion. Yes, we have come across for gases. Rate of diffusion. Please do remember all these terminologies. Rate of diffusion, if you see order of rate of diffusion, CO2 is more diffusible gas, then comes SO2, then comes SO3, sulfur trioxide, then comes PCl3. This is having more diffusible property. Next is vapor density. Vapor pressure we have seen. It is independent of temperature, vapor density, and has no unit, while absolute density is dependent on temperature. The isotherm of carbon dioxide was first studied by Thomas Andrews. Please do remember 1 calorie is equal to what? 4.2 joules. 4.2 joules, or 1 kilocalorie is equal to 4,200 joules. Okay, the gas which has least mean free path has maximum value of A, and it is easily liquefiable and has maximum value of Boyle's temperature. Critical temperature is less than Boyle's temperature, which is less than normal temperature. Okay, for critical constants, compressibility factor, for all these critical constants, compressibility factor is less than 1. Okay, then fraction of the molecules which possess a particular velocity at particular temperature, it is always constant. V by T, we know, according to Charles' law. What does thermometer does? It is used only for measurement of small differences in the temperature. Okay, and that thermometer is called as Beckham thermometer. Boyle's temperature, I'm saying some of the points here. Boyle's temperature is always greater than critical temperature. Next, dry air. Dry air is heavier than wet air. Dry air is heavier than wet air. CO2, carbon dioxide, due to its high density than nitrogen and oxygen, it does not form lower layer of atmosphere. So density of carbon dioxide, yes, is higher than nitrogen and oxygen. Therefore, it will not come into lower layer of the atmosphere. Yes, the size of the weather balloons we have seen under laws, different laws we have seen, it keeps on becoming larger as it rises to higher altitude, because pressure decreases, therefore density also decreases. Gases above critical temperature, there are some gases, they have some names. The gases above critical temperature and under high pressure, yes, they are called as supercritical fluids. They are called as supercritical fluids. So gases above critical temperature and under high pressure, they are called supercritical fluids. These fluids, they are used for very fast separation of mixture into components. For example, I'll tell you, carbon dioxide, its critical temperature is 30.98. Above 31.1 degrees Celsius and above 600 bar pressure is used to remove caffeine from coffee beans. It is used to remove caffeine from coffee beans. Yes, it is called supercritical fluid. It is called supercritical fluid. Yes. So these are some of the important terms. Even a substance in its gaseous state, a substance will be in its gaseous state below critical temperature, and substance becomes vapor above critical temperature. Yes, so below critical temperature, below critical temperature, it is, so a substance below critical temperature is called vapor, and above critical temperature, it is called gas. Yes, so it is called gas above critical temperature. It is called vapor below critical temperature. Yes, so this is all about the states of matter, wherein we have discussed everything regarding gaseous state and some of the physical properties of liquid state. Yes, so hope I have cleared all the concepts in this topic. In the next video, we'll discuss the multiple choice questions related to this topic. I suggest you all, please practice all the concepts, and if any formulae, please do go across them. We have so many relationships according to all the different gas laws or ideal gas equation or van der Waals equations. Go through them, which will help us to solve the multiple choice questions based on this topic. For now, thank you.